This is a very nice geometry problem from the 2009 IMO, the International Math Olympiad. We have triangle ABC with circumcenter O, and then we construct points P and Q on the sides of CA and AB, and then we construct their midpoints, and then we construct a circle around these midpoints, and they tell us that PQ is tangent to the circle, and we have to prove that OP equals OQ. Go ahead and try this yourself and see what you come up with. The first thing you should notice is that the point O is really odd in this problem because everything we do doesn't involve O at all except at the end where they give us the condition to prove that PO equals OQ. So how are we going to use this condition of PO equals QO with the circumcenter of ABC? So to do this, we think about distance to the center because P to O is distance to the center. And when we think about distance to the center, we think power of a point. So let's try power of a point and see what happens. So the power of P with respect to the circumcircle of ABC will be equal to the distance to the circle squared, so that will be PO squared, minus the radius squared. And here the radius is the radius of O, circle O. Similarly, we can write power of Q. So the power of Q will be equal to QO squared minus R squared. So in order for OP to equal OQ, the power of these 2 points must be equal. And this is really important because the power of P and Q can be written in terms of the lengths AC and AB. So we can rewrite the power of P as AP times PC. And that must equal the power of Q, which is equal to AQ times QB. Okay, so now we have an equation to work with. Now that we have this equation, we can use the midpoints now. We can use K, L, and M. Because notice that K is the midpoint of PQ, and L is the midpoint of CQ. So therefore, PC must be equal to KL times 2. And similarly, KM times 2 equals QB. So now let's try substituting PC and QB into our original equation and see what we get. So we have AP times KL equals AQ times KM. We eliminated the 2 because they're on both sides. And now rearranging this equation, we get AP over KM equals AQ over KL. And this is the key equation we've found, because notice that this is a similar triangle condition or a similar triangle equation. This ratios right here tell us that in order for OP to equal OQ, the triangle APQ must be similar to triangle KLM because of the ratios that we obtained from this equation. Okay, so now all we have to do is to show that these triangles are similar. Let's try angle chasing. So first, notice that KL is parallel to AC because KL are the midpoints of triangle PQC. So it must be parallel. Similarly, KM is parallel to AB. So that gives us angle LKM equals angle PAQ. So we've found one angles that are congruent to each other. Now we have to show that AQP is equal to KLM. So angle AQP, let's just name this alpha, and let's try to angle chase our way over to angle KLM. We just established that KM is parallel to AB. So that means that angle AQP must be congruent to angle QKM. And from here we can conclude that KLM must be equal to alpha. And that's because of the condition they give us that line PQ is tangent to the circle. And when you have a tangent circle like this, then these angles are equal. So there we have it. We've proved that triangle APQ is similar to triangle KLM because the angles are all congruent.